Welcome back from Thanksgiving. I hope everyone had enough turkey and sweet potatoes and mashed potatoes and green bean casserole and rolls and pumpkin pie. I know I'm still eating leftovers and loving it. All right, so on this short video, I will introduce to you the topic of temperature regulation. I'll cover pages 269 to 275 in your text, and this will cover lectures number 25 and 26 for Monday, November 30th. Let's begin with figure 12.1 from your text. And this is an overview of heat balance, in which is trying to show us how we maintain temperature homeostasis in a very simplistic model. Of course, our average body temperature is about 37 degrees. And this is maintained because, although we do have heat gain, it is balanced by heat loss. So whenever we generate heat by any of our exothermic reactions, any of those reactions that give off heat, we also have to then accomplish an equal amount of heat loss to maintain 37 degree body temperature. Of course, on a very warm day, or if we are exercising, our body temperature might go up to 38 or 39 or 40 degrees, which means that in the short term, we will have gained some heat, and then over time, of course, we're going to have to lose it. An extreme example of the challenge of temperature regulation occurs in the Badwater Ultramarathon, which is 135 miles, and the temperatures can rise up to about 130 degrees. Anywhere up in the 120 degrees range is completely normal for this race. This happens in July every year in Death Valley National Park, which is the lowest elevation in the United States and also the hottest place in the United States. I think they have recently recorded the hottest temperature ever on Earth. And so this is a super tough race. Only 100 or so people enter it every year. Each competitor is required to have a support vehicle, and you can see the extreme measures they take, including wearing all white clothing, lots of water, hats, and often you'll see them walking on the white line because it's cooler than the asphalt, which can get to 170 or 200 degrees. So I'll refer to this race now and then as we keep talking about temperature regulation over the next few lectures. The next section of your book talks about temperature measurement during exercise. And so we'll first point out that there are two areas in which we like to know the temperature. The first one is the deep body or the core temperature, and we also have the skin temperature, also called the shell. Your deep body or core temperature refers to sort of those organs that are located on the inner part of the body, all of your viscera, your brain, and we can typically estimate what that might be by measuring the rectal temperature or at the eardrum or the esophagus. And to measure the esophagus, you'd actually swallow only partially a thermistor that would just be resting halfway down your throat, right? And that would generally occur in the laboratory. A recent development in temperature measurement has been the ingestible temperature sensors that then have a sensor system, and so that you actually swallow the sensor and it sends a signal to a receiver that's outside the body. And so, for example, football teams and soccer teams, all of the players can have their temperatures measured at the same time as long as you have a computer that can read the temperatures on the sideline. For skin temperature, this is going to be lower than your core temperature. And typically at room temperature, the skin temperature might be 4 or 5 degrees less than your deep body temperature. But in some extreme conditions, say it's really cold outside and you have bare skin, your shell temperature, your skin temperature might be 20 or 30 degrees cooler than your core temperature. Common sites to measure your skin temperature would be at the forehead, the chest, the forearm, the thigh, calf, abdomen, and back. And you would simply just take the average of all of those for an average skin temperature. Next, let's cover mechanisms of heat production and heat loss. Let's start with heat production, in which this can be either voluntary or involuntary. Involuntary heat production would be from either shivering, which happens when our body temperature gets too low, or when we're too cold, or non-shivering thermogenesis, which is your typical metabolic processes that occur when you're at rest. This can be enhanced by releasing catecholamines like epinephrine and norepinephrine, or also the thyroid hormone thyroxine, which controls your metabolic rate. The voluntary heat production, of course, now occurs during exercise. And since we are only 20 to 30% efficient, we know that 70 or 80% of the energy that we are using for muscle contractions gets lost as heat. So we have an enormous heat load during exercise, and so it's a big challenge for us, especially in a hot day or in a hot environment. Next, let's talk about heat loss. And there are 4 main mechanisms by which the body can lose heat. The first is radiation, which is the loss of heat through UV rays. Infrared rays, not UV rays. So if you are sitting indoors at a comfortable 70 degrees, your skin is emitting infrared rays, and that's your main source of heat loss. However, on a really hot day, you can be actually receiving radiation from either the sun or nearby objects, and you can feel the warmth on your skin. If you're standing next to a warm building, a brick building that's been in the sun all day, you can feel the heat coming from it without even having to touch it. That is infrared radiation warming your skin. So radiation is a major form of heat loss at rest, but in some conditions can also be a form of heat gain. The second heat loss mechanism is conduction. This is when heat is transferred from the body to cooler objects that are in direct contact with the body. For example, on a cold day, you're sitting on an aluminum bleacher watching a sporting event. You can feel how you are losing heat through your body into that surface of the bench. That would be loss of heat by conduction. Again, this could be a possible means of gaining heat as well. If the object is really warm and you touch it, you will absorb heat from that object, and so it's not necessarily only heat loss, but is typically. The third mechanism for heat loss is convection. This is actually just a special case of conduction, and it only involves water and air molecules. And so in this case, air and water molecules can be in contact with your skin. They will absorb heat, but the difference here is now that they can move away from your skin to be replaced by cooler molecules. And so it's a very fast and effective way for heat loss. You can think of standing in front of a fan. Lots of convection is occurring and you feel cooler. Or if you jump in a swimming pool, the cool water is absorbing heat from your skin and is actually a very efficient way to transfer heat. In fact, convection in water is about 25 times more effective than convection via air. Just like the other 2 mechanisms for heat loss, convection can also be used to gain heat. Obviously, if you think of sitting in a hot tub at 102 or 104 degrees, you will be gaining heat and your body temperature will increase. The last form of heat loss will be evaporation, and this is when water evaporates from the surface of our skin. This actually takes a lot of energy to go from the liquid phase to the gas phase, and so it takes a lot of energy as heat away from our skin and is very effective at cooling. At rest, this is maybe only 25% of our heat loss, but during exercise, especially in a warm environment, it will usually be the main mechanism for heat loss and the only way we can compensate for this large heat load that occurs during exercise. Keep in mind here that it is the evaporation of the water that accounts for heat loss, not just sweating. So if you are sweating, and say it's on a really hot and humid day, and the sweat falls off your skin rather than evaporates, then you have lost no heat. There is no heat loss for that. It has to actually evaporate. For evaporation to occur, there has to be a vapor pressure gradient between the skin and the air. And so if it's a very hot and humid day, that is, the environment has a very high vapor pressure, the gradient between your skin and the environment may be very low, and so therefore that's conditions that do not favor evaporation. And so the sweat on your skin will not evaporate very readily. It will stay there, and you will not be losing much heat, which is why you get so hot and it makes exercise so difficult on these hot and humid days in the summertime. Conversely, if the relative humidity is very low, then that will be a large gradient in the vapor pressure between your skin and the environment that will readily favor evaporation to occur. So if you're even in a hot environment somewhere like Arizona where the environment is really dry, you can easily, the sweat will easily evaporate from your skin and you can lose lots of heat that way. I'll finish up these pages of reading with figure 12.3 from your textbook. This is just a nice summary of the heat exchange mechanisms during exercise. And you can see the runner here whose body core temperature looks fairly high with a red coloring. And you can also see all of the mechanisms for heat loss and heat gain sort of on this figure. The squiggly lines, squiggly arrows, show heat loss mechanisms, while the straight lines, straight arrows, show ways in which the body will gain heat during exercise. For heat loss mechanisms, we can see the evaporation of sweat as well as respiratory gases. We have convection, we have radiation, and we have some blood flow creating some convection. We can also see mechanisms by which we might gain heat. Of course, the major source of heat is going to be the heat from contracting muscles, but you'll also get thermal radiation from the sky and the ground, as well as any solar radiation if it's a sunny day. That concludes the first lecture for temperature regulation and the first few pages then of Chapter 12.